Right, one more math problem on the chemical equilibrium ice table sheet. This is problem number 6, and this one's a little bit different because instead of solving for K, we're going to solve for the concentration of one of our reactants or products, doesn't matter which. And so just like the previous problems, we need to ID that it's an equilibrium type problem. Well, it says the word equilibrate, so there's the text cue in there. It says that we're solving for the concentration of NO after it's allowed to equilibrate. And it says that these two quantities are allowed to, which implies that these are initial values. That gets us to the idea that we're going to need an ice table for this. And on this one, I didn't have one provided because I wanted you to go through those steps of creating an ice table and not just expecting one to be there if you happen to have an ice table type problem. So you still need to have your substances involved in the equilibrium equation. All of these are acceptable to have in our expression, so we can put them into our ice table. And then this time we still have I, C, and E. And again, I like to give myself that physical boundary of reactants and products so I know where I'm adding and subtracting quantities. Again, you also need to have an expression for this. So in this case, products, your concentration of nitrogen monoxide squared are going to be over your N2 to the first and your O2 to the first. It tells us that we're going to start out with equal quantities right here, 0.375, 0.375. And then, of course, because they're allowed to equilibrate, which means that implies that there isn't any of the nitrogen dioxide to begin. And so we're going to start by subtracting x, and then we're going to increase by 2x. And then based on the text of the problem, that's all we have. We don't know anything else. And so we have 0.375 minus x, and we have 0.375 minus x, and then we have 0 plus 2x is the same as 2x. So I got this by saying 0.375 plus a negative x, so that adds together to make this small little expression right there. Then the last thing, remember, we can evaluate how big x happens to be. Is x important compared to the size of our initial quantity? And one way to evaluate that is by looking at the K value. And so because K is so small, that tells us that this reaction stays mostly over here and very, very little product is made. And if our reaction is staying mostly as reactants, that means that the amount of reactant we have when we're done doesn't change that much. And so what it means that if we're at times 10 to the negative 4 or a smaller K value, then the amount that we're shifting over to the product side is so small that the amount that we take away here is basically the same, or basically nothing, pardon me. So that means that our concentrations are essentially the same. Are they the exact same? No. But what this does is this gets us out of having to use the quadratic equation, which is kind of nice when we do these math problems. So then I can substitute these numbers into my expression, and I now have 1 times 10 to the negative 5th is equal to, if this is going to be 2x squared, the whole thing needs to be squared, which gets me to 4x squared, divided by, I have 0.375, times 0.375. And now I have an option. I can either square root both sides, because that'll get rid of the 4 and turn it back to a 2 and get rid of this and get rid of one of these, since this is the same as really 2x squared over 0.375 squared. So if I square root this whole thing, I can get rid of that, but then I need to also square root that side. Or I can just bring both of these items over to the left-hand side, divide by 4, square root that answer. Either way, I will get to the point of x equaling, I think the number is about 5.9 times 10 to the negative 4th. Then the thing is that I'm looking for this concentration. It says, what's the concentration of NO after it equilibrates, which means this is the box that I want. And that box is the concentration of NO, which is equal to 2x. So I need to take this number times 2. And once I get done with the rounding, I end up with the number 1.2 times 10 to the negative 3rd molar is my final concentration. Hope that one helps.